Right now, you are sitting on a rock hurtling through space at 670,000 miles per hour, completing a journey of 584 million miles every single year without you feeling a thing. That rock orbits a nuclear furnace 1 million times its size, a star so vast that 1.3 million Earths could fit inside it. That furnace is one of 400 billion stars spinning through a galaxy so vast that light itself needs 100,000 years to cross it. But here is what will shatter your mind. Our entire galaxy, with all its billions of worlds and countless civilizations that might exist, is nothing more than a single grain of sand in an ocean containing 2 trillion other grains. If you enjoy journeys that change how you see reality, hit that like button and subscribe. Picture yourself standing in the middle of New York City at midnight, surrounded by the glow of millions of lights and the hum of a metropolis that never sleeps. The lights stretch endlessly in every direction as far as your eyes can see. A sea of illuminated windows and street lamps stretching to the horizon. Buildings fade into darkness at the horizon, their silhouettes marking the edge of the city. Now imagine that cityscape extending not just to the next state, but across the entire continental United States, every inch covered in lights and buildings and human activity. Then stretch it across the Pacific Ocean toward Asia and keep going across Europe, Africa, and Australia. Keep stretching it around the entire circumference of Earth, wrapping the entire planet in a band of continuous city light. Then multiply that distance by 6 billion. You have just visualized the width of our galaxy. Scientists confirm through precise measurements that the Milky Way spans 100,000 light years from edge to edge. 1 light year alone equals 6 trillion miles. This means our galactic home measures 600,000 trillion miles across. Writing out that number in miles would require a line of zeros stretching from your house to the nearest grocery store. But here lies the first shock to human intuition. Despite this mind-crushing scale that defies all earthly comparison, our galaxy represents merely the first step in a cosmic ladder that climbs toward infinities our brains cannot process. Our galaxy, immense as it is just one island among 2 trillion such islands floating in the cosmic ocean, and each one is separated from its neighbors by millions of light years of near-perfect vacuum so empty that a single atom per cubic meter is considered crowded. Every single point of light you see twinkling in the night sky belongs to our galactic neighborhood. The fuzzy band of stars cutting across dark skies reveals the edge-on view of our spiral arms, which contain hundreds of billions of suns, each one a potential center of its own planetary system. We live inside this cosmic city, embedded within its structure like a single cell inside a massive organism, completely unaware of most of what surrounds us, and most of what surrounds us is completely unaware of us. From our position roughly 26,000 light years from the galactic center, we observe star formation regions where new suns ignite from collapsing gas clouds in spectacular displays of gravitational compression. Every year we witness stellar nurseries where gravity sculpts molecular clouds into burning spheres over millions of years, a process so slow that we can only catch snapshots of it happening across the sky. Ancient red giants expire in spectacular supernova explosions that seed space with heavy elements, the raw materials for planets and life itself, scattering the products of nuclear fusion across thousands of light years. All of this cosmic drama unfolds within our local galactic theatre, a continuous cycle of birth, life, and death playing out across millions of light years. Yet, what makes this scale truly disturbing is not its enormous size, but what it represents. Our galaxy forms just one unit in a hierarchy of structures that grows increasingly vast and incomprehensible. Each level of cosmic organization dwarfs the previous one by factors that render human experience utterly meaningless. Standing on Earth and contemplating galactic distances feels like an ant trying to comprehend the size of North America. The ant can sense that something vast exists beyond its immediate surroundings, but lacks the cognitive framework to grasp continental scales. Humans face the same limitation when confronting cosmic distances. Our evolved brains, designed for hunting on African plains and navigating local landscapes, struggle with scales beyond our immediate environment. This cognitive barrier becomes our first hint that the universe operates on levels far beyond human intuition, and that our brains were never equipped to truly grasp the enormity of what exists beyond our tiny world. Each cosmic structure we discover forces us to abandon our earthbound perspectives and embrace scales that feel more like mathematical abstractions than physical reality. The ancient Greeks believed the stars were holes poked in a celestial sphere surrounding Earth, a comforting vision of a small, ordered cosmos built around humanity. Modern astronomy reveals that our galactic home alone contains mysteries that would have overwhelmed their wildest imagination. Every telescope that peers deeper into space discovers new layers of cosmic organization stretching toward horizons we can barely detect. But compared to what comes next, our galaxy looks like a single room in a cosmic mansion with countless floors extending toward infinity, each floor containing its own universe of wonders. Light moves faster than anything else in the universe, racing through the vacuum at an almost incomprehensible 670 million miles per hour. At this staggering speed, a photon could circumnavigate Earth 7 times in a single second, and a radio signal crosses the distance from Earth to the Moon in just 1.3 seconds. Nothing can outrun a photon racing through the vacuum of space. This cosmic speed limit represents the fastest possible way to traverse distances in our reality, a fundamental barrier written into the laws of physics by Einstein's theory of relativity. Yet, even light, the ultimate speedster of physics, requires 100 Susan years to travel from one edge of our galaxy to the other. Think about what this means for human perspective. The light leaving distant stars in our galaxy tonight began its journey when early humans first learned to make fire, when our ancestors were huddling in caves and discovering the power of controlled flames. Photons, now reaching Earth from the far side of the Milky Way, started traveling before written language existed, before the first cities were built, before agriculture transformed human civilization. These ancient light particles carry information about stellar events that occurred when our ancestors were still discovering agriculture and domesticating animals. Scientists use this light travel time as a cosmic measuring stick. When astronomers observe distant galactic regions, they see them as they existed thousands of years ago. The galaxy we observe tonight is actually a patchwork of different time periods, a mosaic of moments frozen in light. Nearby stars show us recent events. Distant stellar neighborhoods reveal ancient history. We never see our galaxy as it exists right now, but rather as a time-averaged composite spanning millennia. This temporal displacement creates one of astronomy's strangest confirmed facts. Every photograph of our galaxy shows multiple time periods simultaneously. The light from various galactic regions left their sources at different historical moments, creating a collage of cosmic history that we capture in a single image. Looking at the Milky Way means looking backward through time, across a span longer than human civilization, each photon a messenger from a different era. But this journey time becomes even more mind-bending when we consider galactic rotation. Our entire galaxy spins like a cosmic pinwheel, rotating once every 200 million years at speeds that would tear apart anything not held together by gravity. The solar system orbits the galactic center at 515,000 miles per hour, completing one lap every 230 million years. The last time our Sun was in its current position, dinosaurs had only just appeared on Earth, and the supercontinent Pangaea was breaking apart, slowly separating into the continents we recognize today. During light's journey across our galaxy, the entire structure completes nearly half a rotation. The galaxy literally changes shape while light travels between its regions, meaning that by the time the light from one side reaches the other, the galaxy has rearranged itself. Even more disturbing is what this implies about cosmic communication. Any attempt to send signals across our galaxy faces this fundamental barrier. Radio waves and laser beams travel at light speed, meaning galactic communication requires patience measured in geological time. If an alien civilization on the far side of our galaxy sent us a message today, it would take our descendants 100,000 years to receive it, representing a gap of thousands of generations. This communication barrier means that our galaxy can never function as a unified system. Different regions operate independently, isolated by the fundamental speed limit of information transfer, and what appears to be a single cosmic structure actually consists of countless independent zones, each evolving without knowledge of distant galactic neighborhoods, developing in complete isolation over hundreds of millions of years with no possibility of contact. Step outside on a clear night and locate the brightest star in the sky. That brilliant point of light is Sirius, burning 25 times brighter than our Sun with a fierce blue-white intensity that has captivated humanity for thousands of years. It appears so luminous that ancient civilizations based their calendars on its movements and told stories about its significance in the heavens. The ancient Egyptians timed their agricultural cycle by its rising in the pre-dawn sky, knowing that when Sirius appeared before the sun, the life-giving floods of the Nile would soon follow. To your eyes, Sirius seems close enough to reach, with a sufficiently tall ladder, a neighbor in the cosmic neighborhood. The confirmed reality shatters this illusion completely. Sirius lies 6 light-years away from Earth. This distance equals 51 trillion miles. If you could drive a car at highway speeds toward this nearest bright star, the journey would require 300 million years, a span longer than the time it took for reptiles to evolve into mammals, then into primates, then into humans. You would need to maintain 65 miles per hour continuously, since before complex life evolved on Earth, before the first dinosaur laid an egg, driving non-stop for longer than the entire age of multicellular life. But Sirius is practically next door compared to typical galactic distances. Most stars in our galaxy are separated by gaps so vast they defy human comprehension. The average distance between neighboring stars measures about 4 light-years, a span of 24 trillion miles of near-perfect vacuum. In cosmic terms, this represents an almost perfect vacuum punctuated by occasional tiny islands of matter. Astronomers call this the interstellar medium, and it is emptier than anything humans have ever created. To visualize this emptiness, imagine shrinking our solar system until the sun becomes the size of a basketball. At this scale, Earth would be a grain of sand orbiting 26 feet away, barely visible to the naked eye. The nearest star would be another basketball located in a different city, perhaps Denver if you started in New York, separated by over 1,000 miles of empty terrain. Everything between these basketballs contains essentially nothing but empty space, just a few stray atoms per cubic meter, a vacuum far more perfect than anything our technology can produce. This emptiness creates profound implications for space travel between stars. Even traveling at the speed of light, the ultimate velocity limit of the universe, journeys to nearby stars require years of travel through the void. Conventional spacecraft moving at achievable speeds would need tens of thousands of years to reach the closest stellar neighbors, far longer than recorded human history. The vast majority of our galaxy remains forever inaccessible to human exploration, a locked treasure chest of wonders we can see but never touch. The void between stars also explains why alien contact seems so unlikely despite the enormous number of potential worlds. If alien civilizations exist on planets orbiting distant stars, they face the same fundamental barriers of space and time that isolate us. The universe conspires to keep intelligent species separated by gulfs too wide for meaningful interaction, each civilization developing in solitary confinement within its own stellar neighborhood. Scientists have calculated that our galaxy contains roughly 400 billion stars. Yet these countless suns are sprinkled so sparsely throughout galactic space that each one exists in splendid isolation, separated from its nearest neighbor by an average of 4 light-years of emptiness. The night sky creates an optical illusion, making stars appear crowded together when they actually inhabit a realm of cosmic loneliness where the spaces between vastly outweigh the stars themselves. This stellar isolation extends throughout our entire galactic neighborhood. Even the dense central regions of the Milky Way, where stars cluster more tightly than in our outer spiral arm, maintain vast empty spaces between individual suns, with distances measured in light months rather than light years, but still far too great for easy travel. Contemplating these vacant spaces between stars provides our first glimpse into the true nature of cosmic architecture. Matter represents rare exceptions scattered throughout an overwhelmingly empty universe. We inhabit tiny oases of substance floating in an ocean of nothingness so vast that our minds cannot truly grasp it. But this galactic emptiness looks positively crowded compared to the spaces that separate entire galaxies. The gaps between galactic neighbors span millions of light years, making the distances between stars seem cozy by comparison and reducing the Milky Way's 100,000 light-year span to a mere hop across the cosmic void. Imagine counting every star in our galaxy. Begin with the Sun and work your way outward through the spiral arms, counting each red dwarf, each blue giant, each binary system spinning through space, each white dwarf cooling toward darkness. Maintain a steady pace of 1 star per second without stopping to sleep or eat, without breaks or interruptions of any kind. You would finish counting after 12,600 years, a span longer than the entire history of human civilization. From the first cities of Mesopotamia to the present day, repeated many times over. Confirmed observations by space telescopes reveal that our galaxy contains between 100 billion and 400 billion stars. The exact number remains uncertain because dust clouds block our view of distant galactic regions. Dark nebulae hide stellar populations that we can detect only through infrared radiation that pierces the dusty veil. But even the conservative estimate of 100 billion stars overwhelms human comprehension. Each of these stellar furnaces burns with the power of nuclear fusion. Every second, Our Sun converts 4 million tons of matter into pure energy through fusion reactions in its core, generating enough power to supply humanity's energy needs for millions of years. Multiply this output by hundreds of billions of similar reactions occurring simultaneously throughout our galaxy, and the total energy production of the Milky Way exceeds the power consumption of human civilization by factors that require scientific notation to express. Our galaxy is a furnace of unimaginable power, a blazing engine of cosmic creation, yet it is utterly insignificant compared to what lies beyond its borders. Yet this staggering stellar population creates an unsettling realization. Despite containing enough suns to power countless civilizations and enough energy to sustain life across billions of worlds, our entire galaxy represents a minuscule fraction of cosmic existence. Astronomers classify the Milky Way as a medium-sized spiral galaxy. Larger galaxies contain more than 1 trillion stars, dwarfing our home by factors of 10 or more. Smaller dwarf galaxies harbour only a few billion stellar furnaces, barely 1/100th of our galactic population. The probability mathematics surrounding galactic star counts suggests mind-bending possibilities for planetary systems. If even 1% of galactic stars host Earth-like worlds, our galaxy contains billions of potentially habitable planets, each one a cradle for life that might develop independently. Some of these worlds might harbour civilizations far older and more advanced than human society, with technologies that would appear as magic to us. Others might contain life forms so alien that we lack vocabulary to describe them. Organisms based on chemistries we cannot imagine. But what makes these numbers truly disturbing is their cosmic insignificance. Every star we have ever observed, every planet we might discover, every possible alien civilization that might exist within our galactic borders amounts to less than 1% of the matter in the observable universe. Our galaxy, with all its countless worlds, represents a single grain of sand on an infinite beach stretching beyond the horizon. This perspective shift challenges human-centered thinking about our cosmic importance. The ancient belief that Earth occupied the center of creation seems quaint compared to modern revelations about galactic scales. We exist on one planet, orbiting one star among hundreds of billions, in a galaxy that ranks as perfectly ordinary among trillions of similar structures. The 400 billion stars of our galaxy burn with energies that dwarf terrestrial phenomena, releasing more energy in a single second than humanity has consumed in its entire history. Their combined light output creates the glowing band we observe stretching across dark skies, a river of starlight that has guided travelers and inspired dreamers for all of human existence. Their gravitational interactions shape the spiral arms where new stars continue forming, maintaining the elegant structure we see today. Their life cycles seed space with heavy elements necessary for rocky planets and biological evolution, scattering the building blocks of life across the cosmos. All of this cosmic grandeur unfolds within what amounts to our immediate galactic neighborhood. The next level of cosmic organization makes our entire stellar city look like a single house on an infinite street stretching across a continent of galaxies. Look toward the constellation Andromeda on any autumn night. That faint smudge of light appears unremarkable among the surrounding stars, easily missed by casual observers who do not know what they are seeing. Ancient astronomers catalogued it as a nebula, assuming it belonged to our local cosmic neighborhood, a cloud of gas within our own galaxy. Modern telescopes reveal a truth that should terrify and inspire in equal measure. You are looking at another galaxy containing over 1 trillion stars. The Andromeda galaxy stretches 220,000 light-years across, making it more than twice the diameter of our Milky Way. This galactic giant harbours enough stellar furnaces to dwarf our local star count by factors of 3 or 4, containing 3 times as many suns as our entire galaxy. If our galaxy is New York City, Andromeda represents the entire eastern seaboard of the United States, a sprawling metropolis of stars beyond comparison. But confirmed measurements reveal something even more remarkable. Andromeda is racing toward us at 250,000 miles per hour, a speed so great that it would circle Earth 10 times in a single minute. This cosmic collision course was first confirmed through precise measurements of the galaxy's blue shift, which showed Andromeda approaching rather than receding from us, and will culminate in the most spectacular event our solar system will ever witness over the course of billions of years. Computer simulations show that in 4.5 billion years, these two galactic titans will merge in a gravitational dance lasting several billion years, their stars intermingling like 2 oceans meeting. The collision will reshape both spiral structures into a single elliptical galaxy that astronomers have already nicknamed Milkomeda. During this merger, our solar system will likely survive intact. The vast spaces between individual stars mean that stellar collisions remain extremely unlikely even during galactic impacts, with distances so great that the galaxies will pass through each other like ghosts. Instead, gravitational forces will fling our Sun and its planets into new orbits around the combined galactic center, our descendants looking up at an entirely different sky. Yet, what makes Andromeda truly mind-bending is not its enormous size or approaching collision, but what it represents about cosmic distances. The light you see from Andromeda tonight began its journey 2.5 million years ago, a span of time so vast it predates the human genus itself. Early human ancestors, Homo habilis, were just learning to use stone tools when those photons started traveling toward Earth, their primitive hands shaping the first technologies that would eventually lead to telescopes and space probes. They had no fire, no language, no capacity to understand what they were seeing in the sky, living brief lives of survival in the African savanna. The galaxy you observe tonight existed before modern humans evolved, before our ancestors migrated out of Africa, before the first cities rose from the desert sands. This temporal displacement means we can never see Andromeda as it exists today. We observe its ancient past preserved in light that has traveled across the cosmic void for millions of years, bearing witness to events that concluded long before our species existed. The galaxy approaching us right now, the one that will collide with our own, might look completely different from what we observe through telescopes. It could have changed in ways we cannot imagine, and we will not know for another 2.55 million years when the light showing its current state finally reaches us. Even more disturbing is what Andromeda reveals about cosmic scales. Despite being our nearest major galactic neighbor, it lies so far away that light requires millions of years to bridge the gap. This distance represents the smallest meaningful step beyond our local galactic environment. Between our galaxy and Andromeda stretches a void containing almost nothing but dark matter and scattered gas clouds, a gulf so vast that if you tried to cross it at the speed of light, you would die of old age many times over before reaching the other side. This intergalactic space harbors temperatures near absolute zero and densities lower than the best vacuum chambers humans can create. Yet this seemingly empty gulf teems with invisible forces that govern galactic motions across cosmic time. Gravity and dark energy competing for dominance in the great emptiness between the islands of stars. Our galaxy does not drift alone through cosmic space. The Milky Way belongs to a gravitational family called the Local Group, containing over 50 individual galaxies locked in an eternal cosmic dance that has been ongoing since the early days of the universe. This galactic neighborhood spans roughly 10 million light-years across and harbors enough combined mass to bend space and time across vast distances, its gravitational field shaping the motion of everything within its domain. Confirmed observations reveal that most galaxies in our local group are dwarf systems containing only a few billion stars each, cosmic villages compared to the great cities of the Milky Way and Andromeda. These cosmic midgets orbit around the two dominant spiral galaxies, our Milky Way and the approaching Andromeda, like moons circling a pair of binary planets, like planets circling a binary star system. These smaller galaxies follow complex orbital paths determined by the gravitational interplay between the two largest group members, their trajectories twisting and turning through the gravitational potential of the local group. The most prominent dwarf companions are the large and small Magellanic Clouds, visible to naked eye observers in the southern hemisphere as two bright patches of light in the dark sky. These irregular galaxies orbit our Milky Way at distances of 160,000 and 200, 0 light-years respectively, and their proximity makes them laboratories for studying galactic interactions in real time. Scientists have discovered that our galaxy is actively cannibalizing its smaller neighbors. Tidal forces created by the Milky Way's immense gravitational field strip stars and gas from the Magellanic Clouds, feeding material into our galactic disk in a slow but relentless process. This cosmic feeding process has continued for billions of years, with our galaxy growing larger by consuming nearby dwarf systems, and it shows no signs of stopping until nothing remains of its smaller neighbors. But this galactic predation reveals something profound about cosmic evolution. Galaxies do not exist as isolated islands floating through empty space. They inhabit gravitational communities where constant interactions shape their structure and evolution over billions of years, their fates intertwined by the invisible threads of gravity. The peaceful appearance of night sky galaxies masks violent processes that unfold over cosmic timescales, collisions and mergers that transform their shapes and redistribute their stars. The local group itself moves through space as a coherent unit. Our entire galactic neighborhood travels toward the Virgo Cluster at roughly 400 miles per second, speed that would take us from Earth to the Moon in about 10 minutes. This motion carries our local collection of galaxies across distances that dwarf individual galactic sizes. We are passengers on a cosmic vessel sailing through intergalactic space toward gravitational destinations we can barely perceive, swept along by currents of matter that flow across the universe. Even more remarkable, the galaxies within our local group are bound together by dark matter halos that extend far beyond their visible edges. These invisible gravitational scaffolds contain 10 times more mass than all the stars and gas we can observe, an invisible skeleton holding the visible universe together. Dark matter provides the gravitational glue that holds galactic groups together, despite the expansion of space itself, a mysterious substance that has never been directly detected, but whose presence is undeniable. The orbital dynamics within our local group follow precise mathematical laws that govern motion across cosmic scales. Each galaxy traces elliptical paths through space, periodically approaching and receding from its neighbours in cycles lasting billions of years. Galaxy clusters represent the most massive, gravitationally bound structures in the universe. These cosmic cities contain thousands of individual galaxies held together by forces so powerful they distort space and time across millions of light years, bending the path of light itself as it passes through their gravitational field. The nearest major cluster, called Virgo, contains over 300 galaxies and lies 54 million light-years from our local group. A vast collection of stars, gas and dark matter that dominates our corner of the cosmos. Confirmed measurements reveal that galaxy clusters should not exist according to the visible matter we observe. The combined gravitational pull of all stars and gas in cluster galaxies cannot account for the tremendous forces needed to hold these structures together. Galaxies within clusters move at speeds approaching 3 million miles per hour, fast enough to cross the entire United States in a fraction of a second. Such velocities should have scattered cluster members across cosmic space billions of years ago, flinging them into the void like seeds from a shaken flower. The solution to this puzzle required discovering that most cluster mass remains completely invisible. Dark matter outweighs visible stars and gas by ratios of 10:1 throughout galaxy clusters. This mysterious substance reveals itself only through gravitational effects on light and matter, creating a cosmic scaffolding we can map but cannot directly observe. Scientists use gravitational lensing to study dark matter distribution in galaxy clusters. Massive clusters bend space so severely that they act like cosmic magnifying glasses, distorting the appearance of background galaxies behind them, and the amount of distortion reveals how much invisible mass clusters contain. The most spectacular example of dark matter evidence comes from the Bullet Cluster, where two galaxy clusters collided at speeds exceeding 10 million miles per hour. During this cosmic collision, the visible gas clouds interacted and slowed down, heating up to millions of degrees in the process. But the dark matter components passed through each other unchanged, unaffected by the violence of the merger. Gravitational lensing maps show dark matter and visible matter separated by millions of light years, providing direct proof that invisible mass exists independently of stars and gas, a ghostly substance that interacts with nothing except through gravity. Galaxy clusters also serve as cosmic laboratories for studying extreme physics. The hot gas between cluster galaxies reaches temperatures of 100 million degrees, hot enough to strip electrons from atoms and create plasma that glows in X-ray wavelengths across vast regions of space. This superheated material contains more mass than all the cluster galaxies combined, yet remains invisible to optical telescopes. The space between cluster galaxies teems with high-energy particles accelerated to near light speed by magnetic fields spanning millions of light years. These cosmic ray particles create radio emissions detectable by specialized telescopes, revealing magnetic structures that connect distant galaxies within clusters. Galaxy clusters form nodes in an even larger cosmic structure that resembles a three-dimensional spiderweb stretching across the observable universe. Superclusters represent the largest confirmed gravitational structures in our universe. These cosmic formations stretch across distances so vast that light requires hundreds of millions of years to traverse them from end to end. Our local group belongs to the Laniakea Supercluster, a gravitational collection spanning 500 million light-years and containing over 100,000 galaxies, each one a city of stars like our own Milky Way. The discovery of superclusters revolutionized our understanding of cosmic organization, revealing a level of structure that astronomers had not anticipated when they first began mapping the sky in 3 dimensions. Instead of being randomly scattered through space like dust particles in a sunbeam, galaxies arrange themselves in vast networks connected by filaments of dark matter and gas, creating a pattern that resembles the neural networks of the brain or the branching of trees. These cosmic highways channel matter across distances that dwarf individual galaxy clusters, creating a hierarchical structure that extends to the largest observable scales. Scientists mapped our local supercluster by tracking the peculiar motions of thousands of galaxies. Despite cosmic expansion pushing distant galaxies apart, gravity causes nearby galaxies to move toward regions of higher density, like water flowing downhill through a gravitational landscape. By measuring these gravitational flows, astronomers revealed that our Milky Way and millions of neighboring galaxies are all streaming toward a massive gravitational attractor hidden behind a veil of dust. This attractor, called the Great Attractor, contains the combined mass of tens of thousands of galaxies concentrated in a region obscured by dust clouds in our galactic plane, a hidden monster pulling our entire neighborhood toward it. The Great Attractor itself represents only a small component of an even larger structure. Recent observations reveal that Laniakea forms part of an enormous complex of superclusters spanning more than 1 billion light-years. This structure, called the Pisces-Cetus Supercluster Complex, may represent the largest coherent structure in the observable universe, a filament of galaxies so vast that light takes over 1 billion years to cross from one end to the other. The implications of supercluster organization challenge our understanding of cosmic evolution. These vast structures formed through gravitational processes that required billions of years to create the patterns we observe today. Dark matter began clumping together when the universe was less than 1% of its current age, eventually creating the scaffolding along which visible matter organized itself. Supercluster boundaries remain difficult to define precisely because they blend into neighboring structures. Unlike galaxy clusters, which are clearly bound by gravity, superclusters represent looser associations that may be dispersing due to cosmic expansion. Some regions within superclusters continue collapsing under their own gravity, while other areas are being stretched apart by dark energy, stretched between competing forces that shape the largest scales of cosmic structure. The shape of superclusters resembles biological structures more than geometric objects. Laniakea looks like a vast sheet with tendrils extending in multiple directions, similar to neural networks in the human brain, and this resemblance may not be coincidental. As both systems organize through processes that create branching hierarchical structures, steep back far enough from the universe and a stunning pattern emerges. Galaxies do not scatter randomly through space, but organize themselves into a vast three-dimensional network resembling soap foam floating in cosmic darkness. This structure, called the cosmic web, represents the largest scale organization of matter in our universe. Computer simulations confirm that this web-like architecture formed naturally through gravitational processes beginning shortly after the Big Bang. Dark matter started clumping together when the universe was only a few 100,000 years old, creating gravitational seeds that eventually grew into the cosmic scaffolding we observe today. The cosmic web consists of 4 distinct components working together across billions of light years. Dense nodes mark the intersections where galaxy clusters form. Filaments stretch between nodes like cosmic highways, channeling matter across vast distances. Walls form sheet-like structures where filaments intersect, creating vast plains of galaxies. Between these structures lie cosmic voids containing almost nothing but empty space, vast deserts in the cosmic landscape. Scientists have mapped this cosmic architecture by observing millions of galaxies and measuring their three-dimensional positions in space. The resulting surveys reveal that galaxies trace out the edges of enormous bubbles, with void regions occupying bubble interiors. This foam-like structure extends throughout the observable universe with remarkable consistency. The gas threading through cosmic web filaments remains mostly invisible to optical telescopes, but glows faintly in ultraviolet and X-ray wavelengths that reveal its presence. This intergalactic medium contains more mass than all the stars in the universe combined. Yet it spreads so thinly that cubic meters of this material contain only a few atoms, making it the most perfect vacuum in existence. Recent observations have detected the warm, hot, intergalactic medium predicted to fill cosmic web filaments. This material reaches temperatures of millions of degrees while maintaining densities barely above the cosmic vacuum, a paradoxical state that physicists are still working to understand. Finding this elusive component required specialized X-ray telescopes capable of detecting extremely faint emissions from hot gas scattered across the universe. The cosmic web extends beyond our current observational capabilities, suggesting that the structures we can map represent only a small fraction of universal organization. Imagine a sphere of space 300 million light-years across containing almost nothing. No galaxies shine within this cosmic desert. No stars illuminate its darkness. No planets orbit through its void. This empty realm, called a cosmic void, represents one of the most mysterious regions in our universe. The Bootes void, discovered in 1977 by astronomer Robert Kirshner and his team at the University of Michigan, spans 330 million light-years in diameter, while containing fewer than 60 known galaxies, making it one of the emptiest known regions in all of space, a vast desert of nothingness in the cosmic web. When Kirshner first plotted the positions of galaxies in that region of sky during his survey of the northern hemisphere, he found an enormous empty bubble that seemed to contradict everything astronomers expected about the distribution of matter in the universe. The void was so unexpected that his team checked and rechecked their data multiple times before publishing their discovery. If our local group existed within this cosmic bubble, the nearest major galaxy would lie so far away that it would appear as a barely detectable smudge in our most powerful telescopes, and the night sky from Earth would be nearly black except for the faint glow of our own galaxy. Confirmed observations reveal that cosmic voids occupy roughly 80% of universal volume. These enormous empty regions separate the cosmic web filaments where galaxies cluster together. Despite their vast size, voids contain less than 15% of the average matter density found elsewhere in the universe. Scientists initially struggled to explain how such empty regions could exist. Modern research reveals that voids represent natural consequences of cosmic web formation. As matter clumped together along filaments and walls under the influence of gravity, it drained away from the regions that became voids, leaving behind vast empty spaces. The emptiness within cosmic voids creates conditions unlike anywhere else in the observable universe. Temperatures inside voids hover just a few degrees above absolute zero, making them the coldest places in existence. Densities fall so low that individual hydrogen atoms may be separated by distances measured in miles rather than microscopic scales, creating a vacuum far emptier than anything we can produce on Earth. These conditions approach the perfect vacuum that physicists can create only in specialized laboratory chambers, yet extend across hundreds of millions of light years. Yet voids are not completely empty. They contain invisible dark matter that forms the gravitational framework connecting them to surrounding structures. Computer simulations show that void regions contain dark matter filaments too tenuous to gravitationally trap normal matter, invisible threads that create a web within the web, extending cosmic organization into apparently empty space. Galaxies that do exist within voids follow different evolutionary paths than their counterparts in denser regions. Void galaxies tend to be smaller, bluer, and more actively forming stars than typical galaxies, developing in isolation without the gravitational disturbances that shape galaxies in clusters. The isolation within voids protects these rare galaxies from gravitational interactions that would disrupt their star formation processes. The largest known void, the giant void or KBC void, spans 1.8 billion light-years across. This cosmic desert contains so little matter that if our Milky Way existed at its center, we would not have discovered the existence of other galaxies until the 1960s. The night sky would appear almost completely dark, except for our local galactic neighbors, and the universe would seem far smaller and emptier than we know it to be. Point the most powerful telescope ever built toward any tiny patch of apparently empty sky. Keep the camera open for days, collecting every photon that arrives from that cosmic direction. The resulting image will reveal something that should fundamentally change how you think about existence. That tiny region, no larger than a grain of sand held at arm's length, contains thousands of galaxies. The Hubble Ultra-Deep Field, created by combining 800 separate images with 11 days of total exposure time, revealed over 10 zoos and galaxies in a patch of sky covering just 13 millionths of the celestial sphere. Each galaxy in this cosmic census contains billions of stars, many likely hosting planetary systems where life might exist, and each one is separated from its neighbors by millions of light-years of empty space. Confirmed analysis of deep field observations allows astronomers to calculate the total galaxy population within our observable universe. The most recent estimates, based on data from the Hubble and James Webb Space Telescopes, suggest that 2 trillion galaxies populate the cosmic volume we can currently detect. 2 trillion represents a number that overwhelms human comprehension. If you could observe one galaxy per second without stopping, you would need 63,000 years to see them all, a span of time that exceeds the entire history of human civilization many times over. Written out completely, this number requires 13 zeros, 2,000 million thousand, zoos and galaxies scattered throughout observable space. Each of these galactic islands contains its own stellar populations. Conservative estimates suggest that the average galaxy harbors 100 billion stars. Multiplying galaxy count by stellar populations yields a cosmic census exceeding 10 to the 24th power individual stars. This number surpasses the count of grains of sand on every beach on Earth by factors of thousands, meaning there are more stars in the observable universe than there are grains of sand on every beach, desert, and seafloor on our planet. But what makes this galactic abundance truly disturbing is how it redistributes significance in the cosmic hierarchy. Our entire local group, containing over 50 galaxies, represents less than 1/50 billionth of the total galactic population, a vanishingly small fraction of cosmic neighborhoods. The Milky Way, with its 400 billion stars, ranks as utterly typical among the 2 trillion cosmic neighbors sharing our universe, an average galaxy in an average corner of an average supercluster. Recent observations suggest that galaxy counts may actually underestimate universal populations. Improved detection techniques continue discovering faint dwarf galaxies that previous surveys missed. These tiny galactic systems, containing only millions of stars each, may outnumber large spiral galaxies by ratios of 10 to 1, meaning the majority of galaxies in the universe are small, dim, and difficult to detect. Deep field observations also reveal galaxies at various stages of cosmic evolution. Distant galaxies appear as they existed billions of years ago, when the universe was young and star formation rates exceeded current levels, their shapes distorted and irregular compared to the elegant spirals we see nearby. These ancient systems show different structures and compositions than nearby modern galaxies, providing glimpses into cosmic history and revealing how galaxies evolve over time, walk along any ocean shoreline and scoop up a handful of sand. Count the individual grains between your fingers. A typical handful contains roughly 10,000 tiny fragments of rock and shell, each grain representing millions of years of erosion and the slow grinding of mountains into dust. Now expand your count to encompass every beach on Earth. Include the Caribbean islands, the Mediterranean coast, the Pacific atolls, and the Arctic shores. Count every grain of sand on every beach surrounding every continent and every island on our planet. Scientists estimate that Earth's beaches contain approximately 7.5 quintillion grains of sand. Written out, this number spans 20 digits, 7,500,000,000,000,000 individual particles. This astronomical count of earthly sand grains pales in comparison to cosmic stellar populations. Confirmed observations reveal that the observable universe contains more stars than grains of sand on Earth. The 2 trillion galaxies we can detect harbor enough stellar furnaces to dwarf our planetary sand count by factors of thousands. Every time you pick up a handful of beach sand, remember that cosmic space contains thousands of stars for each grain between your fingers, and each of those stars is a sun like our own, potentially with planets orbiting around it. But this comparison becomes even more staggering when we consider planetary populations. Modern exoplanet surveys suggest that most stars host at least one planet, with many systems containing multiple worlds orbiting their parent star in complex gravitational dances. The Kepler Space Telescope alone discovered thousands of exoplanets, and statistical analysis suggests there could be billions of Earth-like worlds in our galaxy alone. If conservative estimates prove correct, the observable universe contains more planets than grains of sand on Earth, multiplied by Earth's total number of atoms. Each of these countless worlds represents a unique experiment in planetary evolution. Rocky planets orbit in zones where liquid water could exist. Gas giants dominate outer planetary regions. Ice worlds harbor subsurface oceans beneath frozen crusts. Desert planets bake under intense stellar radiation. Lava worlds glow with molten surfaces, their rocks turned to liquid by nearby stars. The variety of planetary environments exceeds anything science fiction has imagined, with worlds that would seem more at home in fantasy than in reality. The probability mathematics surrounding these numbers suggest mind-bending implications for life in the universe. Even if life emerges on just one planet per million suitable worlds, the cosmos should teem with biological activity. Some civilizations might have evolved billions of years before Earth formed, achieving technological marvels beyond our comprehension. Others might possess technologies that make human achievements look primitive, tapping into energies we cannot even measure. Yet the vast distances separating star systems create isolation that prevents most worlds from ever communicating with their cosmic neighbors. The speed of light barrier ensures that civilizations separated by thousands of light years can never establish meaningful contact. Each inhabited world develops in cosmic solitude, unaware of the countless other experiments in intelligence occurring throughout the universe, and we may never know if we are alone or part of a vast cosmic community. The universe you can see tonight has boundaries, not physical walls marking the end of space, but fundamental limits imposed by the speed of light and the age of cosmic time. These boundaries define what astronomers call the observable universe, a sphere of space containing everything we can potentially detect using any technology humans might ever develop. Confirmed measurements reveal that this observable sphere measures 93 billion light-years in diameter. This distance represents the maximum extent of space from which light has had time to reach Earth since the universe began, beyond which lies a realm forever hidden from human observation. The calculation behind this cosmic boundary requires understanding both light travel time and cosmic expansion. Light from the most distant observable objects began its journey 8 billion years ago, when the universe was only 380,000 years old, a tiny fraction of its current age. But during the journey time, cosmic expansion stretched the space between source and destination. Objects that emitted light 13.8 billion years ago now lie 46.5 billion light-years away, carried to immense distances by the expansion of space itself. Due to this cosmic stretching, light that left distant galaxies when they were relatively nearby arrives at Earth after those same galaxies have been carried to much greater distances by expanding space. This creates one of the most counterintuitive facts about cosmic observation. The most distant galaxies we can see appear as they existed when the universe was young and small, yet those same galaxies currently exist far beyond our observational horizon, evolved into forms we can never observe directly. The observable universe continues growing larger every day as light from increasingly distant regions reaches Earth for the first time. Each second, our cosmic visibility increases by 1 light second in every direction, revealing new territory that was previously beyond our reach, a slow but steady expansion of our cosmic horizon. Over cosmic time, this gradual expansion of observational range reveals new galaxies emerging from beyond the cosmic horizon, galaxies that have been traveling toward us for billions of years and are only now close enough for their light to reach our telescopes. Yet, this growing visibility cannot continue forever. Cosmic expansion will eventually overcome light travel, causing distant galaxies to cross permanently beyond our observational reach. The observable universe will begin shrinking as expansion carries cosmic neighbors across the cosmic horizon, never to be seen again. Current observations suggest that we live during a golden age of cosmic visibility. The observable universe currently contains more galaxies than at any previous time in cosmic history, yet fewer than will be visible in the far future when expansion isolates us from increasingly distant neighbors. Future astronomers will look out at an apparently empty universe, with no evidence that other galaxies ever existed, and the full glory of the cosmos will be lost to them forever. Space itself moves faster than light. This statement appears to violate Einstein's cosmic speed limit. Yet confirmed observations prove that the fabric of space-time expands at rates that dwarf the velocity of photons racing through the cosmic void. Einstein's relativity prohibits matter and energy from traveling faster than light through space. But space itself faces no such restriction. The universe can stretch its own fabric at any rate without violating physical laws. During cosmic inflation, space expanded so rapidly that regions separated by subatomic distances grew to cosmic scales in less than a second. This distinction between motion through space and expansion of space creates mind-bending consequences for cosmic observation. Galaxies at the edge of our observable universe are currently racing away from us at speeds approaching 3 times the speed of light. Yet these same galaxies are not actually moving through space at relativistic velocities. Instead, expanding space carries distant galaxies along like passengers on a cosmic escalator. The galaxies themselves maintain relatively modest speeds through local space, but the cumulative effect of expansion across billions of light years creates apparent recession velocities that exceed light speed, carrying entire galaxies beyond our reach. Hubble's law quantifies this cosmic expansion through a simple relationship between distance and recession velocity. Galaxies twice as far away recede twice as fast. 3 times the distance means 3 times the speed. This linear relationship continues until recession velocities surpass the speed of light at distances exceeding 14 billion light years. The discovery of accelerating cosmic expansion won the 2011 Nobel Prize in Physics. Observations of distant supernovae revealed that expansion rates are increasing over time rather than slowing down as astronomers expected. Dark energy, comprising 68% of universal contents, drives this accelerating expansion against gravitational forces. Current expansion rates suggest that space doubles in size every 10 billion years. This may seem slow compared to human timescales, but cosmic expansion operates across such vast distances that its effects accumulate to tremendous velocities at large scales. The acceleration of cosmic expansion means that most galaxies we can currently observe will eventually disappear beyond our cosmic horizon. In approximately 2 trillion years, only galaxies within our local group will remain visible to future astronomers. The night sky will appear almost empty, except for our galactic neighbours. At the very edge of observable space glows a wall of ancient light, marking the boundary between visible cosmos and unknowable void. This cosmic microwave background radiation represents the oldest light in the universe, emitted when atoms first formed and space became transparent 13.8 billion years ago. Before this moment called recombination, the universe contained too much free energy for stable atoms to exist. Protons and electrons remained separated in a cosmic soup so dense that light could travel only microscopic distances before scattering off charged particles. The universe was literally opaque, like being inside a glowing fog so thick that nothing could be seen beyond arm's length. When cosmic expansion cooled temperatures below 3,000 degrees, protons and electrons combined into hydrogen atoms for the first time, removing the charged particles that scattered light and allowing photons to travel freely through space. The universe became transparent in a cosmic instant, releasing radiation that continues traveling toward us today. Confirmed observations detect this background radiation, arriving from every direction in space with remarkable uniformity. Advanced satellites measure temperature variations of only a few millionths of a degree across the cosmic microwave background. These tiny fluctuations represent quantum uncertainties from the universe's birth, amplified by cosmic expansion into the seeds that eventually became galaxies, clusters, and the large-scale structure we observe today. The cosmic microwave background serves as humanity's baby picture of the universe. We observe this radiation as it existed when cosmic time measured only 380,000 years compared to the current age of 13.8 billion years, a snapshot of infancy preserved across cosmic time. The patterns frozen in this ancient light reveal conditions when the first atoms formed and cosmic structure began emerging from primordial smoothness. But this radiation wall also marks the absolute limit of electromagnetic observation. No telescope can see beyond the cosmic microwave background because no light existed in observable form before recombination occurred. Earlier cosmic epochs remain hidden behind this wall of ancient radiation, accessible only through indirect detection of gravitational waves or neutrino emissions. Beyond the cosmic microwave background lies a universe we can never see but know must exist. This hidden realm extends backward through cosmic time to periods when temperatures exceeded nuclear fusion cores, and forward through space to distances that may continue infinitely in all directions. Theoretical physics provides glimpses into cosmic conditions before the universe became transparent. During the first 380,000 years, temperatures exceeded those found in stellar interiors. Matter existed as plasma so hot that atomic nuclei could not hold on to electrons. The entire universe glowed brighter than the surface of any star, a roiling sea of particles and energy. Even earlier epochs push physics to its theoretical limits. During the first 3 minutes after the Big Bang, cosmic temperatures allowed nuclear fusion to occur throughout space. Protons and neutrons combined into light elements, creating the cosmic abundance of hydrogen and helium we observe today. This primordial nucleosynthesis occurred when the universe was smaller than our solar system, yet contained all the matter we can currently observe, an inconceivable density that defies our intuition. The first second of cosmic time remains largely mysterious, with theoretical models suggesting that fundamental forces separated during this period as expansion cooled the universe below energy scales where particle physics breaks down. If inflation theories prove correct, our observable universe represents an infinitesimally small portion of total cosmic volume. The region that became our observable sphere was smaller than a proton before inflation began, a quantum seed containing all the matter that would eventually become 2 trillion galaxies. Expansion increased its size by factors exceeding 10 to the 26th power in a fraction of a second, faster than the blink of an eye. Yet this inflated volume still constitutes only a tiny bubble within a vastly larger cosmic structure. Current models suggest that different regions of this larger universe may have evolved under different physical conditions. Areas beyond our cosmic horizon might have experienced different inflation rates, creating domains where physical constants take different values. Electrons might have different masses. Light might travel at different speeds. Gravity might operate with different strengths. These variations could create cosmic regions where stars form differently, where chemistry follows alternative rules, where life develops through unimaginable processes. Each domain might represent a unique experiment in physics, isolated from neighboring domains by expansion too rapid for communication. Some theoretical models propose that cosmic inflation continues in regions beyond our observable volume. New space constantly forms through eternal inflation, creating infinite numbers of observable universe-sized bubbles within an ever-growing cosmic structure. Our observable universe may represent less than 1% of total cosmic volume, and possibly far less than that if inflation theories are correct. Bayesian mathematical models, which are among the most sophisticated tools in the statistical arsenal of modern cosmology, suggest the true universe extends at least 250 times farther than the cosmic horizon we can detect, making the hidden cosmos vastly larger than anything humans will ever observe or explore, permanently beyond the reach of any telescope we could ever build. This calculation relies on measuring the curvature of space across the largest observable scales. If the universe was smaller than our observable volume, space would show detectable curvature like the surface of a sphere. But precise measurements of the cosmic microwave background reveal that space appears perfectly flat across billions of light years. Flat geometry indicates that the universe extends far beyond our observational limits, possibly infinitely in all directions. The region we can see represents a tiny patch within a cosmic structure so large that its curvature remains undetectable across distances spanning our entire observable sphere. This resembles standing on Earth's surface, where the ground appears flat, because our planet is much larger than our local horizon. Conservative estimates based on cosmic flatness suggest the universe measures at least 7 trillion light-years in diameter. This minimum size exceeds our observable universe by factors of 75, meaning that for every galaxy we can detect, at least 5,000 similar galaxies exist beyond our cosmic horizon, forever hidden from our view. But theoretical models propose even larger possibilities. Eternal inflation theory suggests that new space constantly forms through quantum processes, creating infinite numbers of observable universe-sized regions within an ever-expanding cosmic structure. Dark energy, comprising 68% of cosmic contents, accelerates the expansion of space with a force so powerful that it overwhelms gravity across distances larger than galaxy clusters. This mysterious component of reality pushes distant galaxies away from us at ever-increasing speeds. The discovery of cosmic acceleration shocked astronomers who expected gravitational forces to gradually slow universal expansion. Two independent research teams studying distant supernovae in 1998 found that cosmic expansion was speeding up rather than slowing down. This observation earned the 2011 Nobel Prize in Physics and revolutionized our understanding of cosmic evolution. Dark energy behaves unlike any known form of matter or radiation. While normal matter becomes less dense as space expands, dark energy maintains constant density throughout cosmic growth. This means that dark energy's influence grows stronger over time as space increases in volume while dark energy density remains unchanged. Current expansion rates indicate that space doubles in size every 10 billion years. This may seem gradual, but dark energy's constant density means that its gravitational repulsion doubles every time space doubles. Cosmic acceleration, therefore, increases exponentially, creating runaway expansion that will eventually overcome all other forces in the universe. Earth occupies the exact center of the observable universe. This statement appears to place humanity in a special cosmic position reminiscent of ancient geocentric beliefs. Yet this central location results not from cosmic design, but from the fundamental physics of observation and light travel time. Every observer in the universe sits at the center of their own observable sphere. The observable universe is defined as the region from which light has had time to reach a specific location since cosmic time began. This creates a personal cosmic horizon centered on each observer's position, making every location the center of its own visible cosmos. Alien astronomers in distant galaxies observe their own unique observable volumes that overlap with ours in some regions while extending into space we can never see. From their perspective, they occupy the center of the observable universe, while Earth lies near the edge of their cosmic horizon. This observational effect results from the finite speed of light combined with the finite age of cosmic time. Light from distant objects requires billions of years to reach any observer, creating a natural boundary beyond which nothing can be detected. This boundary forms a sphere around each observer because light travels at constant speed in all directions. Most galaxies visible in tonight's sky will vanish from human view within the next 2 trillion years, a span of time that is itself almost incomprehensible, but merely a fraction of the universe's ultimate fate. Dark energy acceleration will carry these cosmic neighbors beyond our observational horizon, leaving future astronomers with an almost empty night sky containing only galaxies within our local group. This cosmic isolation has already begun, and we live in the only era when the full richness of the universe is visible to any observer who cares to look. Galaxies at distances exceeding 14 billion light-years currently recede faster than light speed due to cosmic expansion. Light leaving these distant systems can never reach Earth because space expands faster than photons can travel through it, creating a horizon beyond which the universe is permanently hidden from us. We observe these galaxies only because their light began the journey toward us when they were much closer, before cosmic expansion stretched the space between us beyond the reach of light itself. So what we see is a fossil image of a universe that has already slipped away. Computer simulations reveal the timeline of cosmic loneliness. Within 50 billion years, the Virgo Cluster will disappear beyond our cosmic horizon. The most distant galaxies we can currently observe will fade from view as their light becomes too redshifted to detect. Within 100 billion years, only local group galaxies will remain visible to observers in our cosmic neighborhood. Future astronomers living in the merged Milky Way galaxy will inhabit a profoundly different cosmic environment. Their night sky will contain no external galaxies beyond their local merged system. Deep space will appear empty except for the cosmic microwave background radiation, which itself will become too faint to detect as cosmic expansion stretches its wavelengths beyond instrumental sensitivity. This cosmic isolation creates a disturbing possibility for future science. Astronomers living billions of years from now may have no evidence that other galaxies ever existed. The expansion history of the universe will be erased from observational records. The Big Bang theory might never be discovered because the evidence supporting it will have disappeared beyond detection limits. Every galaxy we see tonight will be gone, leaving nothing but the silent, empty void of an accelerating universe. Future cosmologists will look out at a dark, empty sky and have no idea that their universe was once filled with 2 trillion galaxies, each containing billions of stars. The entire history of modern cosmology will be lost to them. Buried in a past they can never access, recent discoveries in quantum mechanics suggest that empty space contains virtual particles that constantly appear and disappear at subatomic scales. These quantum fluctuations might represent shadows of cosmic processes occurring within the underlying structure of space-time itself. Our entire cosmic neighborhood might be nothing more than foam on an infinite ocean of existence, a brief bubble of order in a sea of quantum chaos, where the very fabric of reality fluctuates at scales we can barely measure and theories we can barely conceive. You are reading these words on one planet, orbiting one star in one galaxy, among 2 trillion cosmic neighbors scattered throughout an observable universe that might be smaller than an atom in ultimate reality. This perspective places human existence within a context so vast it challenges every assumption about significance, purpose, and cosmic importance. Earth measures roughly 25,000 miles around. A tiny rock spinning through space at 67,000 miles per hour around a nuclear furnace that consumes 4 million tons of matter every second. Our Sun ranks as a perfectly average star among 400 billion stellar furnaces populating our galactic neighborhood, a middle-aged yellow dwarf that has burned for 6 billion years and will continue for another 5 billion more. The Milky Way galaxy spans 100,000 light-years while containing enough stellar material to power quadrillions of civilizations. Enough heavy elements to build countless rocky worlds, enough organic compounds to seed life across the cosmos, and enough time remaining for life to evolve and flourish across unimaginable distances in countless star systems we will never visit. Yet our entire galactic home represents just one grain of sand on an infinite cosmic beach, containing more galaxies than grains of sand on every beach on Earth. Each of these 2 trillion galaxies harbors billions of stars, many hosting planetary systems where conditions might support life. Conservative estimates suggest that hundreds of billions of Earth-like worlds exist within our observable cosmic volume. Some of these planets likely developed civilizations millions of years before human society emerged, while others may be teeming with life forms we cannot even imagine. Yet the observable universe itself may represent less than 1% of total cosmic reality. Hidden beyond our cosmic horizon lies a universe potentially extending infinitely in all directions, containing infinite numbers of galaxies, stars, planets, and possible civilizations. Parallel universes might exist where different versions of history unfold according to alternative quantum possibilities. Infinite cosmic hierarchies might contain our entire observable universe as a microscopic component within incomprehensibly larger structures. This cosmic perspective simultaneously renders human existence infinitesimally small and profoundly meaningful. We represent temporary patterns of organized matter that achieve the remarkable ability to contemplate cosmic scales far beyond our evolutionary origins. Humanity developed from simple chemical processes on one small planet. Yet we have discovered cosmic structures spanning billions of light years. We evolved to hunt and gather on African plains. Yet we have mapped the large-scale structure of the universe and detected gravitational waves from colliding black holes. The same cosmic processes that created galaxies, stars, and planets also created the complex chemistry that led to biological evolution and human consciousness. We are literally made of star stuff, forged in nuclear furnaces and scattered through space by stellar explosions. Every atom in your body except hydrogen was created inside a star that lived and died before our solar system formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all came from stellar nucleosynthesis occurring billions of years ago in cosmic neighborhoods far from Earth. This material connection links humanity to cosmic evolution across space and time. We represent the universe becoming aware of itself, matter achieving consciousness and developing the ability to study its own cosmic origins. Despite occupying one tiny corner of an infinite cosmos, humans have discovered fundamental truths about reality that apply across cosmic scales. We have glimpsed the true size of existence, stood at the edge of the cosmic horizon, and wondered what lies beyond. We have calculated the number of stars, mapped the cosmic web, and detected the echo of the Big Bang itself. The universe is not only stranger than we imagine, it is stranger than we can imagine, more vast than we can conceive, more mysterious than our minds can hold, with depths of complexity and scales of existence that may forever exceed the reach of the human mind. And yet we try anyway, driven by an insatiable curiosity that sets us apart from every other species on our small planet. And we are here to witness it, here to ask the questions, here to marvel at the immensity of what surrounds us. And that act of witnessing, of wondering, of trying to understand may be the most remarkable thing any species has ever done in the 8 billion year history of our universe.